Well, hi there. We're going to have a look today at identifying and describing relations and functions and the ins and outs of what makes them either relations and functions. We have a particular interest in functions and not really much of an interest in relations in the way we do maths in methods. Okay, so let's have a look at it. It'll become very clear as I show it to you. Okay, so the first question is, what is a relation? What is a relation? Well, at its most basic, a relation is just a set of ordered pairs. That means x's with their corresponding y's, okay, on a two-dimensional plane. That's all it is, a set of ordered pairs, or x's and y's. For example, we've got the set of numbers u. Now, I better go through this in case you don't get all this fancy terminology. U is, curly bracket means the set of numbers. The set of numbers, and we have these sets of numbers here. We've got 1, 1, 1, 3, 3, 7, and 4 and 7. Okay, now that's a relation. That is a relation. Because there is a relationship connecting x and y. Do you see what I mean there? That's what it's all about. There's a relation between x and y. That's why we call it a relation. So x is what's known as the independent variable, which once chosen fixes the value of y. Okay, so once you've chosen x, y is determined. So y in that sense is called the dependent variable because its value depends on x, whereas x is independent, it's the free agent. It can be whatever it likes, but once you pick its value, y is determined. Okay, get it? Very good. Okay, so there may or may not be, yes, that's right, there may not be a specific rule connecting x and y. If you have a look up here, I mean, who knows what the rule is? I mean, it doesn't look like there's anything much going on. It looks pretty random to me. But there is a relationship between them, yes, but as for a rule, I'm not so sure. Now, here's another one for you. The set of numbers t, which consists of x and y such that y is x minus 2. And x can take the values 1, 3, 5 or 7, right? That is a relation with a rule connecting x and y. Here it is here. Here's the code. Come up with the value of x, pick a value out of the box over here, and once you pick that x value, y is determined. Get it? Good. So u has no such rule evident, as you can see. Up here, looks to be a bit of a mystery as to how you get those y's from the x's, okay? At least we don't know what it is. Now, okay, so if the domain, that is all of the x values which apply to the relation, is not stated, it is assumed to be all of the x values which would make sense, okay? That's called an implied domain. Yes? Good. Okay, there's another one for you. V is the set of numbers x and y such that y is root x. Okay, now that implies, guys, what is the implied domain? Well, root anything is a fuzzy function. It can't be negative, so it can only be from 0 inclusive up to positive infinity. Okay, that's the implied domain of that function. Okay, getting it? Pretty easy, eh? I think so. Now, let's start talking about functions now. What is a function? Well, a function is actually a special kind of relation, okay? So, you get that? All functions are relations, but not all relations are functions, if you like what I'm trying to say. It's like saying that all dogs have 4 legs, but not all 4-legged animals are dogs. So a function is a special breed of relation, pardon the pun. It is a relation where for each value of x which is defined, there is only one possible y value, okay? There's only one y value. You pick an x value, you can't have any more than one y value, all right? That's how it works. For example, now in this situation here, now just have a good look at that. Is that a function? Well, I think not. Because see this x here? X is 1, and there you've got either a 1 or a 3 for the y. No, it failed the test, didn't it? It's not a function because when x is 1, y can be either 1 or 3. 2 values for y, for the one value of x, not 1. So that fails the test. Get it? Good. Now, t, let's have a look at that. Yes, I think that's a function because you only have one value of y for each value of x. Yes, very good. Unique value of y for each value of x. That is a function, isn't it? Even though it's a pretty funny looking function, it's not. It's just dots. X can be 1, 3, 5 or 7. So if you plotted that out, you would just have 4 dots on the xy plane, wouldn't you? You would. Okay, it's still a function though. It still qualifies as a function. Now, here's another one for you. V. We dealt with that on the previous page, actually. That's a function, definitely. And actually, not only is it a function, it's a continuous function, because all the values of x are on a continuum without interruption. That is from 0 inclusive up to positive infinity. Yeah. So that's called a continuous function. Easy way to remember a continuous function is you don't have to take your pen off the page to draw the line of the function out. Okay, no discontinuities. Goody. Now, types of relations. Now, this is really interesting. So pay attention and have a look at this, and I think this will make a lot of things clearer for you as you delve into the land of the function and the relation and how to distinguish whether a relation is actually a function or not. Okay, there are 4 types, 2 of which are functions, 2 of which are not. Okay, one-to-one, that is a function. I'm going to explain this one-to-one business in a minute. There's the second type is called a one-to-many. That is a relation. It's not a function. It fails the test. Okay? Right, next one is many-to-one. Now, many-to-one is a function, yes, and last but not least, many-to-many, which is not a function. That's a relation. So you can see that 2 of them, this one and this one, are functions, and the other 2, this one and this one, relations only. Okay, right. Now, in this expression up here, this one-to-one or one-to-many or whatever we've got there, I'm calling the one to the left-hand side of the word to, the left-hand term, and I'm calling the right-hand term the one to the right of the word to. Okay. Now, what I'm saying is the left-hand term relates to x, the values of x, and specifies how many values of x apply to each distinct value of y. Now that might sound as clear as mud, but you'll get it in a minute when I show you pictorially what this means. It's really, really quite neat. So the left-hand side relates to the x, how many x's there are for a value of y. Now to find whether this term is one or many, you draw a horizontal line emanating from any value of y on the y-axis. Now, I'll show you how to do that in a minute. And it reveals much, let me tell you. If this horizontal line intersects once with the curve, the left-hand term is said to be a 1. If it intersects twice or more, it's said to be many. Okay? Similarly, the right-hand term, this one here, the right-hand term relates to y, and it specifies how many values of y apply to each distinct value of x. Okay, this is analogous to the to this paragraph up here. So let's just say that to find whether this term is one or many, this time you draw a vertical line through any value of x on the x-axis, emanating out of that value of x. Okay, and if this vertical line intersects once with the curve, then that right-hand term is a 1. If it intersects twice or more, it's a many, right? Now, I know that sounds clear as mud. Just watch this. I'll show you some examples of each of these 4 little beasties up here. 1, 2, 3, and 4. Okay, here we go. Now, this one here, if you have a look at that, let's just show you what I've done here. That's just a linear graph. If you draw a horizontal line from any value of y on the y-axis, horizontally out in either direction, and then you see how many times you intersect the curve of the function, okay? So the horizontal line indicates one intersection, so that tells you that the left-hand side of the expression here is a 1. It's a 1, right? And the vertical line, the green line, the vertical line, also intersects once with the curve of the function. Therefore, that term is also a 1, okay? So that's a 1-to-1 function, which means every value of x has only one value of y, and every value of y has only one value of x. It's 1 to 1. They're a special little breed of functions which we use to make inverse functions, as I'll describe in a later presentation. But do you get the deal? Do you get the idea? That's a 1-to-1 function, right? So you're thinking to yourself, well, how could you have anything else? Well, fasten your seatbelts. Here comes the next one. Now, do you see this? Look, doing the same tests here. This one here on the blue line emanating from any value of y, right, outwards horizontally, the blue line intersects once. So that side of the thing over here gets you a 1, right? But the green line, the vertical line, intersects twice. Do you see that? Do you see that? Therefore, that side of the expression is a many. And if you've got more than one value of y for a given value of x, which you can quite clearly see that you have, then it is not a function, guys. It is not a function, because you can only have one value of y for a given value of x if it's going to be a function. So that is a relation, okay? That is a relation. You get me? Good. Let's do another one. We'll draw this one out now. What have we got? Righto, that's an example of number 3. Now, let's do the test, the horizontal line test. Blue line gets us 2 intersections, so therefore on that side of the expression we've got many. Now let's do the vertical line test here, the green line. Yes, that only intersects once. So yes, that is a function, isn't it? There's a 1 there, right? So that is a function. Now, that looks like a common or garden quadratic, doesn't it? Well, they are functions, but they are many-to-one functions, as you can quite clearly see. Okay? Get that? Good. Now let's do the last one now, many-to-many. You're wondering, wow, what would that look like? Well, it's a very common shape. Let me show you. There you are. It's a circle. Okay, so x squared plus y squared equals something or other. That is not a function, guys, because here, look, blue line, 2 intersections. So the left-hand side of the expression is many, and green line, also 2 intersections. So the right-hand side of that expression is many. So that guy is a relation. He ain't no function, guys. Well, I just did a double negative. He isn't a function, yes? So, 1-to-1 function. 1-to-many, no, relation. Many-to-one function, many-to-many relation. So what is the pattern coming out of all this? Well, have a look at the bottom of the screen. If the right-hand term is a 1, we have a function. If the right-hand term is a many, we have a relation. Okay, getting it? Isn't this exciting? Very much so. Now, how do you tell a 1-to-1 function? Because as I was hinting before, we have a very special interest in 1-to-1 functions because they are the members of the function world which have things called inverse functions possible, and we'll describe them in a later presentation. So I'm just going to cover in a bit of detail here what makes up a 1-to-1 function. So really, the way to pick easily a 1-to-1 function is that it moves across the page from left to right. As you increase your x values, it either goes uphill in terms of y or downhill in terms of y, but it does never, ever does both. It's either going up or down. It can level off, but only for one value of x. So it can level off to horizontal, but only momentarily for one single value of x before resuming its original direction. Well, what does all that mean? Well, I'll show you. Now, that is the graph of y equals x cubed. That is a 1-to-1 function because the gradient, where it levels off at 0, at that stationary point of inflection, is the gradient is 0 only at x equals 0, at one single point. Okay? So it still qualifies that there's only one value of y for a given value of x. Okay? You can do the horizontal line test, you'll still only hit one intersection. If you do the vertical line test, you'll still only hit one intersection, okay? If it was flatter, if it was flat for more than one value of x, all bets are off. It wouldn't be a 1-to-1. You get it? Good. Here comes another one. Now this is a traditional looking cubic. That's a many-to-one. You can see the horizontal line gets you a many and the vertical line gets you a 1. So it's not a one-to-one, but it would be a one-to-one if we restricted the domain to either from minus infinity up to and including where the stationary point is there, so that's where x is naught, okay? Or you could also go one-to-one from, if you had the restricted domain from naught up to and including 2, where the second stationary point is, yes? Or you could have one-to-one from x is 2, including 2, right up to positive infinity. So you could split it up into 3 prospective one-to-ones if you restrict the domain, but as it is, it's not one-to-one at all. Yes, get it? Good. Here's coming an upside down quadratic. Now that's many to one, horizontal line many, vertical line 1. Yes, now how would you make that one-to-one, guys? What would you do? How would you restrict the domain? Yes, very good. You would restrict the domain so that you could either go one-to-one for x going from minus infinity up to and including 0, where the vertex of this parabola is, or you could go from 0 including 0 up to plus infinity. Yes, that would make it one-to-one, but not as it is, it's many to one. This little beastie here is a one-to-one. Isn't he nice? A little, a bit of a cubic thingy with not the traditional S-bend shape, I think would be a typical example of that. A negative cubic, yes? Alright, so there you go. Do you see? Are you getting me? Yes? Good. Now I'm going to do an example here. This is the one example on this presentation. It looks ghastly. It's actually very easy. I cooked it up because it looks very typical of the sort of questions you'll get in an exam, which are designed to confuse, and but they don't. They don't confuse, because if you're a bit of a detective with a bit of confidence in yourself, you will win the day every time. So what have we got? We've got a cubic function, which they don't even tell us what it is. Well, actually, I made up this question, so I'm not even telling you what it is. It looks like the function, it's a function such that the domain of from a, including a, up to positive infinity maps onto its corresponding real counterparts, has stationary points at this ghastly looking point and this equally ghastly looking point. They're the stationary points, the local max and min. Now, what we're saying here is, if f of x is a one-to-one function, what is the minimum value of a? Yes, I know. It looks like just the most disgusting question, but no. It's actually very easy. So what you've got to do is just do a bit of detective work. So, how would you do a question like this? You get very practiced at them, believe you me. I'm looking at, see, it looks like I'm looking here. I'm going from a up to infinity, okay? And I've got to find a one-to-one bit. So it's got to be going either uphill or downhill, but not both, okay? So what did I do to tackle this question? What would you do to tackle this question? Well, there's a few things you can do. You can pause the video and have a go if you like. Alright, had a go? Here we go. It looks difficult, yes, but it's actually very simple after you basically do some thinking and maybe some detective work on it, okay? First thing, I notice that there's 2 stationary points, right? Because cubics can have either 0 or 1 or 2, depending on their shape. So this one has a traditional S-bend shape, as I call it, yes? Number 2. Let's just sort out what those dreadful looking stationary points are and restate them in decimal terms by just massaging them a bit on the calculator. And what do we get? Well, what we get is some very illuminating information, guys. So look, if I call that point 1, I call this little one here point 1, and I call this one over here point 2. Okay, therefore this one's x1 and y1, and this one over here is x2 and y2, isn't it? Now, you can see that x1 is less than x2, but y1 is more than y2. So that gives us a shape. That gives us a shape. That's the shape, because you can see that this little guy here, this is point 1 is to the left of point 2 because of the x's, but y1 is more than y2, so it's higher than y2. So what does that tell you? that tells you that point 1 is a local maximum and point 2 is a local minimum. Okay, now look, we're nearly there now. We are nearly there. So what are they asking us in the question again? They're asking us what is the minimum value of A if this is going to be 1 to 1. Well, what you've got to do, guys, is go back as far as you possibly can until from positive infinity, because remember, this thing goes from A up to positive infinity. So go backwards from the positive infinity department as back as you far as you possibly can until it just turns around and goes the other way. That is the minimum value of A possible today. Hooray? Yes. So therefore, for a one-to-one function, we can have, as I've said here, you can have domains of in general, you can have from minus infinity up to and including x1. You can have from x1 to x2 inclusive, or you can go x2 inclusive up to positive infinity. But we are told that the domain goes from A to positive infinity. So that's a giveaway, isn't it? So it's telling you that A is actually x2. Yes, for the minimum value. It can be anywhere. It can actually if they didn't say the minimum value, then A could be anywhere from x2 up, including x2. But they're asking you for the minimum value of A, so it has to be bang on x2. Yeah, which is that value. That's the value there, which is this one up there, right? It's the value of x at the local minimum. That's how you do it, guys. Now, there you go. That's how you work out the land of the relation and the function and all the one-to-one, one-to-many, many-to-one, many-to-many kind of thing, and which ones are functions. If they have one on the right-hand side of that expression, they are functions. Right. I'm going to go now and have a nice cup of tea. Thanks, and do some practice, and you'll get really good at it, and we'll see you next time. Bye-bye.